we were looking at an object, Adler-D function, and we saw that it has this form. I would encourage you to look at the literature and obtain this result, which to some extent we alluded to. Okay, that's the contribution. Beta naught f is the contribution to beta function coming from fermionic loops. And this minus 5/3 comes from using MS bar scheme. Okay, so we saw this result, and this is what I was calling last time as DIR, contribution to D coming from the infrared region, and this is what I defined as DUV coming from the ultraviolet region. Okay, and we see that there is a factorial growth in the coefficients. So you have, even though you have an expansion in alpha s, the coefficients are growing larger as you go to higher orders in perturbation theory. Okay, and also see that there is a, here there is a negative power, so you have an alternating series, so -1 to the n here. This one does not have. Okay, these are some of the features which are present in front of us. Now, question was, what does it mean to give a prediction from your calculation for any observable in the light of this observation, that if you were to keep calculating higher and higher order terms, you are likely to encounter this problem. So one good strategy in case of enormous difficulty is to give up sometimes. So I'll just give up. I will not talk about this because I have enormous difficulty. I'll just do something else. And you will see why that can be a good strategy sometimes. Okay, so since we have given up on this thing, let's erase it. So I'll start with some, so really we are now doing something else, part 2. So I'll start with some notation, and which we are going to utilize in the remaining of this lecture. So I'll say a function f of x is much smaller than another function g of x. Okay, so we say f is much smaller than g of x as x goes to x naught. So there is some point x naught you have in mind, and you are telling the behavior of these two functions, comparing them, and say fx is much smaller than gx as x goes to x naught if the limit of this ratio as x goes to x naught is equal to 0. Okay, that's what I would mean by saying f is much smaller than g. So I'll give you an example, or maybe two. X is much smaller than 1 over x square. Okay, we already have this notion in mind. I'm just making, giving a concrete definition of what it means. So x is much smaller than x naught. You can take the ratio, and you see that if you take the limit goes to 0. So x divided by 1 over x square, that's going to give you x, and limit x goes to 0, that goes to 0. So this statement is correct according to this definition. Second example, x is much smaller than -1. Okay, So it doesn't matter whether there is a plus 1 or minus 1 here. You take this ratio and again you see that the ratio, the limit of the ratio will be 0. Okay, so x is much smaller than 1 according to this definition. So second notation, we say two functions are, okay, let's say fx is asymptotic to gx no as x goes to 0. Okay, so fx is, so this you read as fx is asymptotic to gx as x goes to x naught if, so by this statement I mean that fx minus gx should be much smaller than gx. Okay, where I have already defined the symbol, what it means to say something is much smaller. So you can check if two functions, the difference of them is smaller than g using this criteria, then you say fx is asymptotic to gx as x goes to x naught. And you can also check that if fx is asymptotic to gx, then gx is asymptotic to fx. Yeah.
So it is the ratio is the thing which we are on which
Ratio is the
which
thing.
we are saying.
So we have to, even though we might have some preconceived notions about what I mean by smaller than this or smaller than that,
Right.
we have to rely on the definition. Okay,
Okay.
so you have to be careful. That's the definition we use. But it's also, see, as x goes to 0, x is going to 0, but minus 1 is remaining minus 1. So of course it is smaller, but then by this definition it is. Okay, any other question? So that's the definition of saying fx. So you say fx is asymptotic to g of x as x goes to x naught if the above condition is satisfied. And an equivalent statement of this, I will ask you to check it yourself. Equivalent statement is that limit x going to x naught is 1. Okay, so this ratio fx over gx is 1 if x goes to x naught, and if that is the case, then you say this function f is asymptotic to g, and you can check that if this is true, then g is also asymptotic to f. Okay, and these two are equivalent statements, fx minus gx being much smaller than gx, or take the limit. So I'll give you some examples of this. So take fx to be e to the x plus x, and take g of x to be e to the x. And let's look at x going to infinity. Okay, x not equal to infinity. So I'm interested in the point x naught. So these two functions are asymptotic to each other by the definition. Okay, if you take the ratio and take the limit, it will give you 1. Is that okay? You agree to that? But note that being asymptotic to each other does not mean that they are approximately the same, because the difference between the two is x, right? And x goes to infinity as, the difference goes to infinity as x goes to infinity. So even while I am saying the two functions are asymptotic to each other at x goes to infinity, it does not mean that they are approximately equal, because the difference between them is infinite. Is that okay? So e to the x plus x is asymptotic to e to the x as x goes to infinity. Okay, but the difference does not go to 0. Okay, so you have an infinite difference or a very large difference for any value of x, a large value of x. Okay, so this might have already given you some idea about what we mean by asymptotic. I'll give you one more example. X square and x. Take these two functions x square and x. Now as x goes to 0, both these functions are going to 0, right? So both of these are going to 0, so they are going to be approximately equal for very small values of x, but these are not asymptotic to each other. Okay, you can check. I should have gotten 1 if according to my definition. So two functions can be asymptotic to each other even while the difference is going to infinity, and they may be asymptotic, not asymptotic to each other even though they are approximately equal at a certain point. Okay, so this is a little counterintuitive if we are not already used to this definition. So let's spend some time with differential equations. So let's take second order differential equation. That's generic equation. I'm looking at homogeneous equations, and you can take a point x naught and then classify whether the point x naught is a ordinary point of this differential equation or a singular point, and if it is singular, it could be a regular singular or irregular singular point. Have you, I would believe most of you have studied these things, okay, but nevertheless I'll just in a moment I'll write this. So if Px and Qx are analytic at a point x naught, then we call these as the point x naught as a ordinary point. Otherwise, if any of these is not analytic at that point, it's called a singular point. Okay, if these quotient functions are not analytic, if Qx times x minus x naught square and Px times x minus x naught, both of these are analytic functions at x naught, then you set this point x naught as a regular singular point. Okay, if this is not true, if either of these or both of these are not analytic at x naught, these products, then you say it's an irregular singular point. and probably you already know the behavior of solutions at around x naught for ordinary singular points will be of the form of, there will be analytic functions. So you can do a Taylor expansion. Okay. If you have a regular singular point, then the solution behavior would be like a Frobenius form, right? X minus x naught to the sum alpha times an analytic function, and then other solutions will also involve product of logs. Okay. So I'm more interested in differential equations with irregular singular points, and so the behavior of solution in the neighborhood of that irregular singular point. So we are going to do a local analysis, because doing global analysis is very difficult. I'll be content with knowing how the solution behaves in the neighborhood of that irregular singular point. So goal is okay? So goal is clear, huh? Okay, maybe I'll just, even though we are going to work with this, I'll just write down what the solutions are, the form of solution. So you'll have two solutions, second order differential equation. One solution will be of this form, where Ax is analytic, alpha could be non-integer, so you may have, you will have algebraic similarity at x naught, and another solution will be of okay plus some bx. Okay, that's the nature of solutions in the neighborhood of a regular singular point. Okay, let's move on to irregular singular point.
The Px and Qx are the analytic at x0, then how the Px into x minus x0 singular, like
No, other way around.
it has 0, no?
No. So that's the differential equation. Choose a point x naught. Choose some point. Check whether these two functions are analytic or not. If both of them are analytic at that point, then that point is an ordinary point. So in the neighborhood of that, the solutions will be analytic, and you can do a Taylor expansion. If any of them is not analytic at that point, then that point is a singular point. Now you could classify further between ordinary singular and irregular. If these products are analytic at x naught, then you say it's a regular singular point. Otherwise, it's an irregular singular point.
How the singularity is coming, that is I'm not actually not understanding.
So because see, if a function is not analytic at a point, that's a singular point.
But you define that P and Q are the analytic at x0, so that means it.
I didn't, no. If it is not. No, I didn't define. I'll show you. So I'll give you one example. Maybe it will be clearer. Okay. And I'm not claiming there. Depending on what is happening at x naught, you tell whether it's singular or not. Okay. So up to here we are fine. Now I'll give you an example of a differential equation which has a irregular singular point, and we are now going to be interested in looking at the solution in the neighborhood of that point. So let's take so you see q is 1 over x cube, right? If I compare this with that one, minus 1 over x cube, correct? Minus 1 over x cube times, so I'm looking at point 0 now, x equal to 0. I'm interested in knowing about x equal to 0. So I take 1 minus 1 over x cube multiply with x square, right? If that is analytic, then that would be a regular singular point, because x equal to 0 anyway you have a pole, right? You have a singularity. So you have a singular point. I want to know whether it is regular singular or irregular, and clearly this condition, this product is still singular, which means that point is irregular singular point. because minus 1 over x cube times x square is minus 1 over x, and this is not analytic at x equal to 0. Okay. Now we want to find a solution to this one in the neighborhood of x equal to 0. Now typically what happens is you can make a substitution which will work. Now why it should work, I don't have an answer. Probably no one has. But it works, and which also means a lot of time it will not work. Okay. So you can make a substitution y equal to e to the s, and we want to determine what s is. Okay. If you are lucky it will work, if you are super unlucky it might not work. Okay. So let's assume we are lucky, and now whatever we are going to do is a lot about being lucky and unlucky, because there is no there is no formalism that you take this differential equation and you do these steps and you are going to get the solution. That doesn't happen. So otherwise our life would have been much easier. So y is e to the s. So let's choose. If let's say we are lucky and substitute it in here, so you get x cube agreed. So y is e to the s, that's here, x cube, taking the first derivative will give you s prime e to the s, taking second derivative will give you these terms. Okay. So I will factor out e to the s and I am left with this equation. Okay, I missed, no, that's fine. So that's the differential equation I get, and it is not any better than the previous one. It's same problem, we have not achieved anything. This is okay, I have simple differentiation after. Now often it happens, if you are lucky, and a lot of time you will be, that the second derivative of s is much smaller than, and you know what I mean by much smaller, the definition, okay, s prime square. If you are as x goes to, in this case x goes to 0. So typically when x goes to x naught, your irregular singular point, this condition is going to be satisfied, not always but a lot of times, and in this case x equal to 0 is our irregular singular point, and let's assume that this is true. Let's assume we are lucky and that is true. Okay, that's an assumption now. So I have two assumptions. It will be of this form and that condition is also true, right? So if that condition is true, let's look at this differential equation. Now we have to work only with s. So I can write s prime square minus 1 over x cube is equal to s double prime. Okay, that's this relation, this equation. And because s, I am assuming s double prime is much less than s prime square as x goes to 0, that's the assumption. This implies that s prime square is asymptotic to 1 over x cube. Okay, so this implies this. You can check that this is indeed true, because Let's say whether this is true. So remember the definition of being saying much asymptotic 2 is I take the difference of the two and then compare with this thing, right? And see whether that is much smaller. So you can verify. Maybe I'll just show it to you, check, confirm the verification of my previous claim. So S prime square being asymptotic to this means should be much less than S prime square. Okay? But then this is S double prime. So it is true. Okay. So now I have this equation. S prime square is asymptotic to 1 over x cube, which means S prime is asymptotic to 3/2. I do an integral and say S is asymptotic to, sorry, I am doing the integral. And the question will be what should I write here? I think people have decoupled. What's the question there? We are doing integral. Huh? That you divide, right? So you get a 2 in the numerator. Correct? So there are two such things. So you see where we are now. We said let's try a solution of this form. So now I have two solutions, and not surprising because that's the second order differential equation. Y equal to e to the 2 over root x and e to the minus 2 over root x.
The previous sign you put plus minus.
Where?
S prime.
Thank you. Is that okay? So where we are, and some functions. Okay, there could be some functions because all I am doing is asymptotic analysis, right? These are not equalities. These are asymptotic analysis. So there could be some function. So I am happy that I have now at least some knowledge about the local behavior of the solution. So y behaves as e to the or as x goes to 0. Okay, I'll work with this one. Similar analysis you can do for the other one, and I'll be looking at x going to 0 plus, so that I don't have to worry about this taking imaginary parts. Okay, just for simplicity. So I think we can be happy, even though we are not doing our usual way of dealing with equalities and getting a solution. We are doing asymptotic analysis, but we know about the local behavior of this solution to some extent. That okay, it will behave like e to the 2 over root x. And you can already see that this is not a series expansion like Taylor expansion or Frobenius expansion. It has a 1 over root x. Okay, it has essential similarity. Okay, let's proceed further. So good, I could be happy with this. But since we are QCD community or Hierarchy community, we will not be happy. We want the next one. Okay. So let's make an improvement. Let's say S of x is 2 over root x. Okay, I am putting equality here. Okay. some c of x. And now I want to know what c of x is. And again I will do the same kind of reasoning. I will get a differential equation for c by taking this y equal to e to the s, putting it in the original differential equation and getting a differential equation for c, and again saying maybe this guy is smaller than that guy, assume it, and get an estimate for c and check that that estimate is consistent with your assumption. Okay, I mean what you get is consistent with your assumption. So I'll show it to you. It's easy, but it's going to be very useful for us. So substitute this in the differential equation, and that will give you, maybe even while I am writing you can already do it, it will give you this. So I'll show you roughly these terms. So your differential equation is y double prime minus 1 over x cube. Right, that's the differential equation we have. Yeah. So y is e to the s. Actually, instead of using this, you should use the differential equation for s that I had written here, this one. Okay, we don't need to work with y, we need to work with s. And the s is this one. So you see, differentiating this twice will give you 1 over x to the 5 halves, second derivative of this. Okay, then you already had 1 over x cube, and these are the other terms coming because of squaring this, the first derivative. So that's what you get. Okay, so that is what we have now. And remember, we are doing asymptotic analysis. Since we said Sx is asymptotic to 2 over square root of x, that Cx should be much smaller than 2 over square root of x, right? So we have already, because of our original assumption, Cx should be much smaller than 2 over root x. Now if I take a derivative of this, now taking derivatives, integrals and all these things, I am doing as if they are all permitted, but one has to be careful and check whether that's correct, and I'll give you the reference from which I am doing this so that you go through the relevant part and make sure that these operations are allowed. Okay, but I'll proceed as if they are perfectly fine, no issue with them. Okay, so C should be much smaller than 2 over root x because that was the leading behavior we were already taking, which means the derivative should be much smaller than 1 over x 3 halves. And this implies that if I look at c prime square, so I am estimating this term, you have a c prime square here. Okay, so c prime square, which is c prime times c prime, will be much smaller than, I take one c prime factor from here. Okay, so c prime square is much smaller than c prime divided by x 3 halves. As x goes to 0. Now if I use this in here, this information in this equation, and I get 3 halves 1 over x to the 5 over 2 plus c double prime is asymptotic to 2 over x 3 half c prime. Okay, so these two terms are here, that is this term, and as I have already argued, the c prime square is much smaller than this. I am leaving that term out, and in that asymptotic analysis, this equation or this equation becomes this asymptotic relation. Is that okay? Okay, we are about to see something, about to see at least something now. Nice or not is a different thing. So, since c prime is much smaller than x 3 halves.
Excuse me.
Yeah.
I might be wrong, but there should be a sign, negative sign, like when you go from C to C prime.
Where?
The last step, like Cx to C prime x. And same with the integration also, like that.
Here, the minus sign there?
Yes.
That minus wouldn't matter. You remember I gave you an example with the minus x being much smaller than minus 1? Yeah, same thing.
Okay. And same is the thing with the integration also, like that plus minus should have gone to minus plus. Is the same thing?
Yeah.
Okay.
I am just saying there are these two solutions.
Okay.
I am not saying that one corresponds to this one and this one. That one. So, we are here, and because c prime is much smaller than 1 over x 3 halves, c double prime, if you take the derivative, is much smaller than this. With that, I can reduce this relation, this asymptotic relation, to 3 over 2, 1 over x 5 over 2 is asymptotic to as x goes to 0 plus. Now that's an relation involving only c prime, and you have 3 half and 5 half here. So you can do an integral. So I will just do it. This is 3 over 4, 1 over x is asymptotic to c prime, right? So c prime, sorry, c is asymptotic to 3 over 4 log of x. Is that okay? Just doing an integral of 1 over x, that gives you log of x. So what I have done is, I started y equal to e to the s. First I made first estimate of s, it was 2 over root x and minus 2 over root x, that minus 2 over root x I am leaving out, I am looking at only one of the solutions. Then I refined the estimate for x and I said s I will take as 2 over root x plus some c of x. Now I have made an estimate of c of x and it turns out to be a log of x. So at this stage, I should again try to improve my estimate of x. Okay, and again set up a differential equation for d following the same procedure, make similar analysis, say this guy is smaller, much smaller than that guy, and get a asymptotic relation which is manageable for you, and get dx. Now exercise, I have done 2 parts for you, you can do the third part for yourself. Show that s of x is this. So when you do this, repeat the analysis, you will get s of x to be these two terms, of course, plus a constant term, constant as x goes to 0, plus another function h of x, where h of x would have the following behavior. As x goes to 0, that function goes to 0. Before h of x, all other terms, neither of these were going to 0, rather they were singular. Then at some point you end up with a constant, and then the corrections have behavior that they vanish as x goes to 0. That's what you will get. And in fact, you can determine what h of x would be. Again, repeating the same argument. Also, exercise. Again, repeating same arguments. Show that h of x is asymptotic to minus 3 over 16 square root of x as x goes to 0. Okay, so you see this goes to 0 as x goes to 0. Okay, so now we are happy. We know how solution looks like. It will be e to the 2 over root x. Okay, I'm looking at one of the solutions. And then you have what? Plus 3 over 4 log x, right? In s, so I'm writing e to the s. Can you read out what's the next thing? Plus delta. That's what you have. So this is what? E to the 2 over root x. E to the 3 over 4 log x is x 3 over 4. Then you have e to the delta, some constant. That's some constant. And e to the hx. But hx goes to 0. So e to the something which vanishes, which I can write as where epsilon x is a function which goes to 0 as x goes to 0. You can be happy at this point of time. You have the local behavior of the solution, even though we didn't know how to exactly solve this. Okay, so some result we have. And of course, there will be some constant here. So that's the behavior. Any questions? Now I showed you e to the x plus x is asymptotic to e to the x as one of the examples, right? The difference between the two is very large for large x. It's infinite. We are doing asymptotic analysis. Imagine you could find the solution exactly or numerically for each value of x or some values of x. You determine numerically the solution and then you have this fitting. And here you have asymptotic analysis. And you are trying to look at how good this is. You might want to know how good is your estimate. And you might also want to know how close the estimate is to the, let's say, numerically evaluated one, or if someone could solve exactly to that one. So I'll show you that one, that result, what it is like. So I'm giving you solution. So to do numerical analysis, you will need boundary conditions. So take y1, y at 1 equal to 1 and the first derivative to be 0, okay, and then do a numerical evaluation. Now when you do a numerical evaluation, so I gave this to my master students and they produced the plot. So the result varies over several orders of magnitude. I'm forgetting how many, probably 4 or 5. I might be wrong with that thing. But the result in the range 0 to 1. Okay, since this is important plot, I will give it here. So 0, 0.25, 0.5, that's x-axis. Here is the numerical result for y of x. So when you do a numerical estimate, you find that C will come out to be 0.14. One four three two something. Okay. Now y of x, as I said, we are trying to find it in the neighborhood of this point. Okay. Our asymptotic analysis is valid here. I am giving you result up to 1, and as I said, the y varies over several orders of magnitude in this range. But if you take the ratio of y to our this expression, so we'll leave out c, x3 half e to the 2 root x okay, take that ratio. I am leaving out these parts, epsilon I am not taking, and what you find is this, something of this form. Okay, so that's 0.12, that's 0.14, meaning even though your y is varying over several orders of magnitude in this range, and you have made an estimate, an asymptotic estimate in the neighborhood of x equal to 0, you have a very good estimate of result, because this result is varying only by 15 to 20% from 0 to 1, right? So you have really good estimate of the behavior of your solution. These terms, this factor, okay, which, so you can see the pieces in S which do not go to 0 as x goes to 0, they give you the dominant behavior, okay, the leading behavior. So this is the leading behavior of your solution, because that's coming from the terms which do not go to 0 in x, okay. So that's called the leading behavior. Okay, so I think we can be very happy that our asymptotic analysis is giving you results which are in such fantastic agreement with the numerical evaluation.
That S double prime is much smaller than S prime.
Yeah, it will not always, no, it will not be always true.
So it might deviate if you don't make this assumption, no?
No. So I am saying in those cases where this assumption is going to work, that's the estimate,
This
but
will work.
it will not always be the case. So you may have situations where that assumption is wrong. But here you have to check the consistency that your assumption is indeed correct. Okay? It should not be inconsistent. That consistency has to be
That
checked.
will work out if it's, it will be, but the solution that that it is good approximation for the the full solution is
That
actually
also is-
subject to the whatever assumption that you made, no?
Okay. See, many things have gone into this. Any of it could break and this will not be the outcome. But generally it will work, or let's say most of the times it will work. But there is no formalism to say these are the steps and that is what you'll get. We don't have.
Yeah, I agree. My question is actually that asymptotic analysis are really good, but can we trust it for any generic case, actually for all values of x?
For all values of x? No. Not
In this
here.
example, it is very good.
No, you cannot. So it is,
It might break somewhere, no?
it is, yeah. So it is good up to here. We are lucky because all that we did was in the neighborhood of that. So there is no reason why that far it should be working. So probably if
Because of that condition, maybe it's working up to that.
okay, so let's how to say? Let's keep that question in mind, whether it's working for that reason or not. And I'm about to say something which will answer your question to some extent. So what Ravi is saying is, you have made some assumptions, and that is why it's working over such a wide range, so far away from x equal to 0, right? That's what you're trying to say. Yeah, I mean, in the question, in the question, that's the observation. Okay, and that's a good observation. And let's see what I can say about it. I was about to say something which will answer that. Okay, so 15 to 20% deviation from numerical result, even though the result itself is varying over several orders of magnitude. So that's a very, very good estimate. Now let's do what a perturbation theory person would do. Include, so this is this curve, okay. Include not just up to here, let's take h of x also. H of x I gave it to be minus 3 over 16 square root of x, right? It went to the exponent here, and you have e to the h of x, which is I am writing as 1 over 1 plus epsilon. So your estimate including h is now, so I want to give you another curve on the same plot. So it is y of x divided by x 3 over 4 e to the 2 over square root of x 1. Can anyone help me? Students? Minus okay, thank you. That's all of what we have calculated now is in here, right? So I take that ratio and plot it on this. So blue might not be so much visible. Okay, let's try. You will get something of this form. The improvement, you will see, you expect an improvement in the agreement with the numerical result. So the ratio actually improves, something of this form. Is it visible? Yeah, it's visible. Okay, I don't know how much this is, but something of this form. So you have a better agreement, but the point up to which the agreement was good has now shifted here. So that depends on the value of x and how many terms you have taken. I think that is what your question was. Okay, so we have a better agreement, and we can be very happy that we know the behavior of the solution around x equal to 0. So you can actually do more, a lot more, and repeat this analysis and find the entire expansion for epsilon x. Okay, that's doable. So I'll give you as an exercise, and you can look into the book how to do it. Show that is asymptotic to okay, I'm not confident about one sign, but I'll write the solution. I thought I knew, but I can recall. So some constant okay, these are your original things. Then you have 1 plus something. So I'm writing this down as series. Okay, so you had epsilon x. So you have, I'm writing down a series expansion of epsilon x here. It comes out to be gamma n minus half n plus 3 halves pi 4 to the n and factorial. That's what you get. Now you might want to stare at the result that I have written and see whether it makes you happy or unhappy. So you have x to the n half n equal to 0, 1, 2, so forth. So these things go to 0 as x goes to 0, which is expected, right? Because we were only left with those terms which go to 0. And these are the coefficients you can determine. Any observation about this? N goes from 0. That's correct. That n equal to 0 will be the 1 there. So that's the asymptotic estimate I have for the result. Okay. Now take n to be large. If you take n to be large, those halves and 3 halves do not matter anymore. So that's gamma n, that's gamma n, that's n factorial. That's n factorial, that's n factorial divided by n factorial. You have coefficients which are growing as n factorial as you include more and more terms, right? You have a factorial growth again. I was avoiding this problem. I started by saying that let's give up on our quest and do something else, but it has showed up again. Is it fine? But then that should worry you. It again means if you kept calculating, at some point you will have results which will not make any sense. There will be no agreement with those numerical estimates, right? You had a good agreement with numerical estimate if you had only the first term, 1 here, or the second term, but then it's clear if you keep including, you are going to go very far away from this and eventually diverge completely. You will have no prediction at all, right? That's the situation we were in initially. How are we doing with time? Okay. So this is a divergent series or factorially divergent series. But we do have an observation that no matter what is going to happen as you include higher and higher terms, at some point it was giving good estimates. And at some point even that estimate was getting better upon including the next term in the perturbation series. That much is clear from this example. Okay, so that's our observation. Any questions? Okay, so I will, before proceeding, I'll give you, okay, my notes are almost over for this lecture. So I'll give you some definition. So I'll define what asymptotic power series is. So to say you have an asymptotic power series, by itself this means nothing. You always say that a series is asymptotic to a function and at some point. Okay. So as x goes to x naught, this series is asymptotic to that function. Without reference to a function, there is no meaning of saying this series is asymptotic. Okay. So a power series is said to be asymptotic to a function y of x as x goes to x naught. Okay, you can write this way or even better this way. So this series is asymptotic to this function as x goes to x naught. Thank you. If the difference of yx and the first capital N terms in the series, this sum, okay, so take this difference, add up to only the first n terms or n plus 1 terms, not everything. Look at the difference. If this difference is much smaller than s minus x naught to the n, okay, that's capital N, as x goes to x naught. Okay, so you have included first terms up to a capital N here, and you are saying that difference is much smaller than, and I told you what it means to say much smaller than in the beginning, x minus x naught to that capital N, but not just for any n, for every n. If this is true for every n, every capital N, then you say this is asymptotic, this series is asymptotic to this function as x goes to x naught. Okay, that's the definition. And for this, series need not converge. You don't require any convergence. An equivalent definition, which will be again very useful, you can check that based on the definitions we gave earlier, an equivalent definition is asymptotic to, the difference is asymptotic to so imagine you have this series expansion that you have done, okay, and you keep first n terms. After the first n, after these first n terms, the next term has a coefficient which is non-zero. If that coefficient is non-zero, then this is what is sitting here, a n plus 1, x minus x naught, n plus 1. If that coefficient is 0, go to the next term, then that guy is sitting here. So m is that number larger than capital N for which a m is non-zero for the first time. Is that okay? And for every n. So this has to be true for every n. If it is true for every capital N, for every such difference that you can make, it is asymptotic to the next term, then you say this series is asymptotic to the function that you have. Sorry?
So in the second line there will be an an less than x minus x.
No,
naught.
listen, this here, this,
Here no, and the above line. In the less than expression.
no, that is n.
Only then.
N, yeah.
Not an times x minus x naught all to the power.
Or you can put that also, it will not matter. Yeah. Okay, so that's what is so you can, as I said, you can put that one also. So you see, if you have found an asymptotic series and you want so I am assuming that I know y of x, okay, there is y of x known, and I have done an analysis, found an asymptotic expansion to it, and from my asymptotic expansion I want to have an estimate which is very good to the real result, okay. What I should do is, or the closest that I can come to is determined by this, okay. So there are those coefficients sitting. So you see, as you include, so initially you will see a behavior which is getting better and better, as you saw there also, but eventually at some point of time it will start becoming worse, which you know because of the divergence, these coefficients are divergent. So what you do is, if you take So you identify in the series that term which is the smallest, has the smallest value for a given value of x. Once you have identified that term, take the term previous to that and start from 0, the first term, and add up to this one. That sum is in here. Okay? Then that will be much smaller than your smallest entry in that series, smallest term in the series. That will provide you the best estimate from your asymptotic expansion, including one term higher or two terms higher or including one lesser will make this estimate go worse. Okay, so this is telling you how you should use asymptotic series. Now, if our field theories were giving asymptotic series, if we do not know, because to even say whether this series is asymptotic, I should be knowing the function itself, right? Without knowing the function, without knowing that that full result, I do not know whether there is no meaning of saying something is this series is asymptotic too. But suppose it existed, then the best estimate you would get not by including more and more terms, but rather finding the term which is the smallest in your expansion and stopping just before that and including everything else. Is that okay? So that will be your best perturbative estimate. This is what you see from here. Agreed? So we are not doing a mistake by calculating terms in perturbation series. It's not like, what are you doing? It's just infinite. No, but the assumption is that it is asymptotic. If it is asymptotic, okay. But now imagine. Okay, I'll give you an exercise and maybe show it next time. But imagine you have in not quantum field theory, not particle physics, but let's say you're playing maths and having fun, and for some equation, some differential equation, or in some context, you have obtained an entire asymptotic series in all the infinite terms, the entire, like in this case here. And then I come and tell you that, oh, it's all useless because only the first few terms up to which the smallest one you encounter, only up to that is relevant, rest is useless. That's what it seems to imply from what I have said so far. Okay. Now I will show you in the next lecture that you have information contained in those remaining terms, and they are very useful, and they are going to be useful in our quantum field theory, and that's why we are talking about this. So we will see what to make out of those remaining terms. Okay. So the thing which I will show you is, given this divergent series, okay, if I add naively, you are going to get infinity. If you try to sum it up, it's infinity, right? It's n factorial divergence, so it's infinite. Nevertheless, we will add everything up, so I'll have to tell you what I mean by the sum. So I'm going to sum up the divergent series and give you an answer, and there's something nice there because of which Shantan asked me to give these lectures, and I have been reading about it. Okay, so we'll see what that is. Okay, I'll stop here.
I just want to ask, is there a way to find out the smallest term without knowing the y of x, like without knowing the function itself? Can you figure out like which term where to stop at?
No, how would you know?
That's what I'm asking. Is there any? No.
How would you know? Unless you have calculated all the terms, you wouldn't know. So here you can know, right? Here you know all the terms. So you just look at each term and see which one is the smallest. But unless you have all the terms, you don't know.
I just had an question. In experiments, we know like y as a function of x in different ways. So, how many of them are required? Is there any calculation where people have checked this or getting some kind of function form or something?
Yeah. So we'll actually that's the maybe I should save it for next time because saying anything will reveal some of the. I'm trying to create some suspense so that there's some excitement. Yeah. So the answer is precisely for those things for which you wanted me to talk.